Welcome to our lecture on energy transition, how to switch from conventional energy supply to renewables. The lecture and the exercise takes place online. You have videos for that. If you have any questions, you can consult me or Mr. Möller. You find his email address there and the telephone number. Also, there are consulting hours via this Zoom link there. Let's start. This is the University of Paderborn, the Faculty of Electrical Engineering, Informatics and Mathematics. We are the chair of Electrical Energy Technology and Sustainable Energy Concepts. Our research areas are the sustainable generation of energy and the sustainable use of energy. We do wind power monitoring and wind power prediction, yield prediction and optimization of photovoltaics, microinverters. We test conversion efficiency, but also do a yield comparison. Energy efficient buildings, decentralized energy systems, virtual energy storage, demand side management, load shifting via remote control of loads. Flexibility options, so we check adaptability to solar and wind generation. Give you now an overview of the lecture. Today is the first lecture, so I will give you an overview. We discuss the units, the aims, climate change, and the sectors of energy transitions and the related tasks to that. Next lecture we will talk more about conventional energy supply such as coal, gas, oil and nuclear. We learn something about simple thermodynamics, about the so-called capacity factors. We compare the different energy systems, the grid levels, grid composition, daily and seasonal load curves. Then we start with the renewable energies. First, we'll discuss about the fluctuating renewable energies, such as solar energy. First part of that is to learn something about solar irradiance. Then we come to the conversion of solar energy via solar concentration and solar thermal energy conversion. Then we go into the direct conversion of sunlight into electricity. That's called photovoltaics. We learn something about the principle and its characteristics. Then we discuss photovoltaic systems. So that's not only the generating part, but also the conditioning part. Then we will go to wind power. We learn something about the principle of wind energy, its parameters, converters, historical and actual development, sizing study, including converters, storage and transmission systems. Then we come to the renewable energies with a constant power output, for example, stored hydropower. Then we will discuss about geothermal energy, then about biomass power, and then we come to energy storage. Part 1 will teach you about technologies, parameters and costs. It includes lithium-ion batteries and the power-to-gas principle. Then we come to the second part, which will discuss the role of storage inside a 100% renewable energy system, how we can minimize storage necessities via the complementarity of power sources, also called anti-correlation. Then we will see the perspectives and feasibility of energy transition. We will compare different countries and regions, the diesel generating substitution, conventional versus smart energy systems, grid control, balancing power via smart demand side management. Then we'll talk about the simulation tools like Homer, PV Syst, Metronome or Energy Plant, which puts it to a larger scales. This will be a guest lecture by Professor Meschede. And at the end, we will discuss about some practical issues on energy transition. First, let's talk about the units of energy. So we have basic unit, the ISE unit is a joule, or 1 kilojoule is 1000 watt times seconds, so 1000 watt seconds. And this is 1 kilojoule. Formerly, the unit calories was used. 1 kilojoule is 0.2388 kilocalories. Or in terms of kilowatt hours, it's a relatively large unit, so 1 kilowatt hour is 0.000278 kilojoule. If you look up some tables and so on, for example, the BP Energy World Outlook, you will still find energy units which are related to fossil fuels, just as the burning value of kilogram coal equivalent or crude oil or cubic meters of natural gas or methane. These are found here on the right side. And here also you find this matrix, the cross factors, how to convert one energy unit into the other. Very often, for example, at air conditioner, you find still the unit, a British thermal unit, which is about equivalent to a 1000 kilojoules. Important, the abbreviations, the kilogram means 10 by a power of 3, so multiplied by 1000. Abbreviation is a small k. Please don't use a big K because this is the abbreviation of Kelvin. For mega, it's a big M, so this is a factor of 1 million or 10 to a power of 6. Don't mix it up with a small m, because a small m would mean it's milli, that is a 10 to a power of -3. So there is a difference between those two, 10 to a power of 9. So this makes a huge difference just if you mix up the small m and the large m. Giga, also use a big G because small gram would symbolize gram. Giga is 10 to a power of 9. Tera, only with one R, so it's not tera like the ground, it's tera, the Greek word, and this is 10 to a power of 12, the big T. Peta, 10 to a power of 15. And exa, this unit we will use if we come to a global world energy consumption. This is 10 to a power of 18. We possibly won't deal with units smaller than milli. So this micro, nano, pico, femto and atto is just here for completeness. Definitions of energy. First we will see what primary energy means. This is the entire energy contents of all energy carriers used. Often only a small part of that energy is finally available at the consumer. This is so-called final energy. To give you some examples, for example, electricity. If you get electricity from a coal power plant, more than 60% of the primary energy are wasted. Or if you drive a car, a gasoline car, about 70% of the primary energy, that means the energy content of the gasoline, is wasted. The final energy, as already mentioned, is the useful form of energy at the consumer. For example, it's electricity. We stay at electricity. Electricity is the most versatile form of energy. Can be transformed in any other form of energy with a relatively high efficiency. For example, into mechanical energy for transportation with an efficiency of about 90%, or into light via LEDs, or directly into heat, or even better via heat pumps. Electricity can be transported easily, but storage is more difficult. Here you see the world's energy consumptions. As you may see, the share of conventional fossil fuels is still very large, such as oil and coal, but the renewables are increasing steadily, especially if you consider that it's mostly useful form of energy, for example, electricity. This is a case for hydropower, for photovoltaics and for wind power. Here you see the relative share of types of energy consumption. You see that formerly oil has been the most dominant source of energy, but it's decreasing steadily. Also, coal played a very big role quite a long time ago, and it's going down. And you see on the bottom the hydroelectricity, which remains relatively constant, maybe with a small increase. Also, you see nuclear power, which has its peak at about 20 years ago, and the steady growth of other forms of renewable energies, such as wind and solar, which reached about in 2018 the level of nuclear power. We have to deal with an increasing population and also with an increasing electricity consumption. The consumption is increasing to a bigger scale than the population because we see a shift in terms of energy towards electricity. We will discuss first about the aims and the motivations to carry out the energy transition, particularly here in Germany. First idea was to abandon nuclear power. Why? Because a secure operation cannot be guaranteed, even in industrialized first world countries, and this is true much more for many other countries. No commercial insurance for operations, so the liability is transferred to the government, or in other words, the people. Indirect subsidy by favorable legislation for nuclear operation. We have the problem with the final waste, which is not solved in all countries. We have to consider that 50% of the radiation of plutonium still exists after 12,000 years of storage. Proliferation is a big issue, so many countries you wouldn't consider as safe. And also we have to consider that uranium resources are limited and are not available in Germany, for example. Also, another motivation is climate change, so we want to reduce carbon dioxide and other greenhouse gas emissions. Climate change becomes evident, so we have the melting of glaciers, the rise of sea levels, droughts in many countries, and more weather extremes, so we have more high and sometimes more low temperature. We have stronger and more frequent storms. And this is due to our way of energy consumption, as you saw before when we took a look at the primary energy consumption and we divided between carbon dioxide emitting and non-emitting fuels. You see that only a relatively small share is without carbon dioxide emissions. It's increasing, but still the share is relatively low. Here you see in light blue the development of renewables, which developed quite positively, but the share is relatively low, and nuclear power, which is also sometimes considered as carbon dioxide free, which is stagnating since about the year 2000. This carbon dioxide emissions lead to an accumulation of carbon dioxide in the atmosphere. This has been continuously observed since 1958 on a laboratory on Hawaii. Before the carbon dioxide condense in the atmosphere has been evaluated by ice drillings in the Antarctica. Here you see the error bars. So you see some error bars in terms of time is relatively big, so some 20-30 years. But the accuracy in terms of carbon dioxide concentration is relatively good. So there's only a quite small error bar. So altogether it fits to one curve, and this is increasing heavily. Nowadays it's just 2007. We have now carbon dioxide content in the atmosphere of about 418 parts per million. What does this mean, carbon dioxide? It's not poisonous carbon dioxide, it's indivisible part, it's transparent, but the problem is in the infrared part, it's not transparent anymore. And this has some impact on the Earth radiation balance, as you see here. So we have in average, the incoming solar radiation, 342 watt per square meter. This is averaged all over the season, over day and night. So it's not directly sunlight. If you have direct sunlight, it's in the vicinity of about 1000 watt per square meter. Or if you go above the atmosphere, it's even 1350 watt per square meter. But if you average it out over day and night, the different seasons, constant flow is then 342 watt per square meter. Then a part is reflected by clouds and aerosols. Then a part is absorbed in the atmosphere. This is all, the units are watt per square meter. And some is even reflected by the surface. Sure, if you have a snow surface, a lot of it is being reflected, but there are many dark areas which have a good absorption of the sunlight. And finally, we have an absorption of the surface by about 168 watt per square meter. This heated surface is emitting radiation, as you see here on the right part, but also it leads to thermal. So this means convectional heat flow here. This amounts to about 24 watt per square meter, or even much bigger evaporation. So if you have moist surfaces like in woods or seas, then some part is getting evaporated and transport latent heat into the atmosphere. And from the clouds which are building up here, this is in radiation exchange with space, and a lot of that energy is being transmitted into space, emitted into the atmosphere. So here also part, but also here. And here the right part is the black body radiation. So we have a surface radiation in the vicinity of 350 watts per square meter. And a large part of it is being directly emitted to space, but a part is being back radiated due to the greenhouse gases, such as carbon dioxide, such as methane, and so on. And we are increasing this value now, and so we have more back radiation, which leads to higher heating up of the surface and consequently to higher surface temperatures. Here also more simplified energy flow by MIT. You can do nice simulations. These are the different results centered, but also a significant increase in temperature over the next decades. The Paris Agreement said we shouldn't go above 1.5 degrees Celsius temperature elevations or 2 degrees, but you see all models predict a much larger temperature increase in the next decades. Here you see the actual temperature development. You see already we reached a temperature increase above 1 degree. The temperature is quite correlated to the carbon dioxide contents of the atmosphere, as you see here. This goes back to 150,000 years before Industrial Revolution. You see here that the correlations is quite obvious. Also, you see that the increase of carbon dioxide took place in a relatively large period of time. So this is probably about 1,000, 2,000 years where this increased. And as I mentioned before, now this year we reached the point of 418 parts per million, which is well above that scale. Within a very short period of time, within the last 100 years, we achieved a very high increase, and this is never seen in many years before today. Some people say even 500,000 years this never happened. Some people also say, yes, there is temperature increase, but there's nothing to do with carbon dioxide. It's the sun, because there is a fluctuation of the sun radiation to spots on the sun surface. Yes, there are some variations, but as you see here, the scale of the influence of that spot are rather lower than the effect of the carbon dioxide. So the effects of the temperature increases are more and stronger storms, and this led to natural disaster. Even companies like the Munich reinsurance company, they already set up a task force to investigate that, because they have suffer by this economic damages, at least by the insured economical damages, and this increased a lot during the last decades. What other effects we have here? So we have an effect on food. So if we go above this mentioned 2 degrees threshold, the crop yields will fall, the glaciers will melt, and we will have water shortage, rising seas. So the glaciers, we already observed that even for temperature increase below 2 degrees. Also, we observe now the reef damaging. Go to Australia, the reefs bleaching, and they even have problems with the tourism industry. The natural effect on the fauna and flora in the sea is rather more severe than the effects on the tourism industry. Then we have a species extinction. This already happens. Also, we have storms, droughts, fires, and heat waves. As you see, the large fires in California, in Siberia, or also in the Amazon basin. And there will be even abrupt climate change after 2 degrees, which cannot be predicted nowadays. If we take a look at the world's energy consumption and its resources, so here we have a small red cube. This represents the world's energy consumption during 1 year. In contrast, we have all the resources we have, the traditional resources, for example, here natural gas, the blue cube here. So it will last probably for 20, 30, 40 years, depending on the scientists which made the predictions. The oil resources will last a little bit longer, coal even more longer. Also, uranium resources are quite limited. So if the whole primary energy consumption would depend on uranium resources, they would be depleted in the vicinity of 40 years or so. So in contrast, we have here the solar energy hitting the surface of the Earth during 1 year only. This is much, much more than all resources we have together for all times, and a much, much bigger, exactly 14,500 times bigger than the world's energy consumption during 1 year. If we use converting technology, for example, photovoltaics with a relatively moderate efficiency, of 10% only, and we want to feed the whole world with solar photovoltaic electricity, we would need only a relatively small share of the desert of Sahara, as indicated here. If you do it more on a global scale and distribute these power stations, you come to this picture. So the black dots are original scale power plants we need here. And this would be equivalent to about 18 terawatt of installed power. And costs would be in the vicinity of less than 20,000 billion euros. Okay, that's not little, but if you take a look what is spent for the wars on oil and so on, it becomes, this is about the same vicinity. Here we'll discuss it a little bit later. The advantage of that distribution is you balance out the difference in the irradiation values in night and day, but also the seasonal changes. So if you put some of those large-scale power plants on the southern hemisphere. This is quite interesting. This is a prediction by Shell, which is a mineral oil company in the year 2000. And you see here the business perspectives. You see here that a mineral oil will reach its peak according to Shell nowadays in the year 2020 and will decrease then, and all the renewables will increase significantly. Additionally, Shell expects that the nuclear power will increase, which didn't take place in the last 20 years. But it's quite interesting to see that a company which really relies on fossil fuels doesn't see a big future on that. Cost of renewables, so this is 18 years ago. And you see here that it was expected that wind power will cost in 2010, 2020 in the vicinity of 3 to 4 cents per kilowatt hour. And for example, photovoltaics in the year 2020 will cost about 10 cents per kilowatt hour. Same about geothermal is expected. Okay, it's cheaper, 3 cents to 2.5 cents per kilowatt hour. Solar thermal will decrease also in that vicinity, and biomass probably will be in the vicinity of 5 to 6 cents per kilowatt hour in the year 2020. So quite interesting if you take a look what actually happened. Now photovoltaics reached 1.4 cents per kilowatt hour in sunny locations. Even in Germany, we have 4 cents per kilowatt hour. So this is only half the price what it expected for the year 2020. And this is a study made in the United States, which usually has a higher solar irradiance than Germany. Since 2012, most of new power plant capacity are renewables. That's also quite interesting to know. So most investments go into renewables. It happens in the power sector nowadays, or even since 2012. This is an update of last year. Here you see that from the nominal power, about 117 gigawatt of new power plants are set up as solar power plants, 61 gigawatt as wind power plants, only 18 gigawatts have been invested in coal power plants, gas power plant 30 gigawatt, hydro 15 gigawatt, other kinds of renewables like biomass power plants 5 gigawatt. You don't see here nuclear because the net capacity increase was 0. So there have been a couple of nuclear power plants newly installed, but also some more have been dismantled, and therefore there are no new net capacity in nuclear power plants last year. Come back to Germany a little bit. So Germany's plan is to reduce consumption and ramp up the renewables share. As you see here, this is the final energy and demand in Germany scenario. This is energy consumption. The efficiency will increase because we will use more electric cars, which are much more efficient with primary energy than gasoline or diesel cars. And here also the same applies for industry, for heat production. For example, if you use heat pumps, they are much more efficient than burning fuels for heating. And also commercial and households. Good, households, there's expectation some decrease, but not very much. So you see here, and here you see the ramp up of renewables, biomass and waste, wind power and solar power in principle. Here, this is also a scenario by the Ministry of Economy and Energy. So you see here a decrease in conventional energy, a steep decrease in conventional energy forms. Here the fade out of the nuclear power plants finally carried out in 2022. And then also the fade out of the coal power plants and the substitution of them by renewables and by reduction of energy consumption. Here a small shift is expected from the point of electricity consumption because some sectors like mobilities are shifted towards electricity sectors. Formerly they belonged to the transport sector, but now these energy amounts needed there has to be accounted for in the electricity sector. This is the development of the annual share of renewable energy production in Germany. So you see here about 2 decades ago that the share consisted basically of hydropower and was in the vicinity of 5-6% in 2002, or 2002 it was 8.6%, 8.5%, and this year in 2020, at least I have the numbers until 22nd of October, so brand new numbers, has been 52.5% of German electricity consumption has been renewables. We expect that until the end of the year we'll still have about 50% of the German electricity consumption will be via renewables. So this is from last year, 2019. So there 50% has not been reached. It was 46.1%. This is different shares of the different energy sources. So you see the largest share with 24.4% has been wind power. So this amounts even more than lignite or brown coal, which is from the emission point of view rather bad because this is more than 1 kilogram of carbon dioxide is emitted for the production of 1 kilowatt hour of electricity. As hard coal, oil and so on. Uranium, this was still nuclear power amounting about 13.7% for the contribution on the German electricity. Solar was 9%. And a nice overview for the year 2020. As I mentioned already, we are well above 50% up to now, to the 20th of October here. And you have here the share of solar increased. Okay, this was due to the Corona shutdown. The energy consumption decreased in the beginning of the year. But also you see here the wind power amounts significantly more than the lignite power and so on. So this is the expectation or the plan of the Ministry Energy to reduce the carbon dioxide emissions by the different sectors. So as you see here, the largest part is by electricity, transport. They have to do more. It didn't happen a lot, so the cars became more fuel efficient. But on the other hand, people are buying more and especially bigger cars. And so there wasn't in the last year a significant reduction in the transport sector. If you talk about electromobility, yes, it's increasing, but you should always consider the largest part of electromobility is still train system. So if we could increase train system rapidly, we would have here a quick and fast reduction of carbon dioxide emissions in that sector. We have also to think about the structure of the power plants, not only in terms of carbon dioxide, but also in terms of flexibility. So as you see here, that was in 2012, there were some renewables, but the fluctuation inside the baseload power plants have been quite small. If you go to 2020, we have periods of time when almost the entire electricity demand can be fulfilled via renewables. And therefore, the backup power plants have to be able to digest that. This is sometimes not possible, especially nuclear power plants. They cannot be throttled below a threshold of 40% of their maximum power. Also, lignite power plants are not very flexible. There are some efforts to improve that, but still it's a large challenge for the conventional energy industry. Here's the flexibility, the parameters and the players involved, how we can achieve flexibility. We can achieve that by the supply side, sure, we discussed this, but also we can think about how we can have demand side flexibility. This happens already in industry. They get a different energy tariffs depending on the time of day when they use electricity. This doesn't happen at the conventional consumer side. It's not understandable, while many other commodities are related to fluctuations on the market. And this would lead to a much higher flexibility in the market, and this will lead to reduced costs actually to maintain the energy system. Also, market design is related to demand side. So if you have a higher price while there's a scarce of energy, then people would think about whether they can save energy or other way around. If there's a surplus in energy, if you have a windy periods with lots of sunshine, you have more energy than you need, you can offer energy for free. Storage. This also plays a big role to increase the flexibility and system operations also, and T&D, this means transmission and distribution networks. They can also play a significant role, but we come to that a bit later in the lecture. This was about carbon dioxide. We came now to a third motivation to carry out energy transitions. This is the reduction of dependency of imported fossil fuels. So this just consider the costs of wars, so securing oil resources in the Middle East and the problems also related to it. Some people forget about this. Germany contributed about 10 billion German mark for the liberation of Kuwait. The US spent a really large amount of money for the wars in Iraq and Afghanistan, about 1,556 billion US dollar. This was, as I mentioned already, so this is already a share of the money what would have been necessary if you want to set up a global solar energy supply. Another effect which cannot be accounted directly into money, but if you depend on fossil fuel, you always have to take care on the countries which supply fossil fuels. For example, Saudi Arabia. There's little complaint about the missing democracy there. If you compare it, for example, to Cuba, which doesn't have any oil, so the pressure there is much higher than to Saudi Arabia. This shows the dependency on imported energy carriers. So here you see hard coal. This is nowadays imported to a share of 88.5%. Petroleum 99.5%, natural gas 88.5%, and uranium 100% imported. So this is the aim of the government, how it should be carried out. This is the increase of renewables. This is already taking place to some parts. And we will go now into the different sectors. So first, the electricity sector. So we will have an increase in electricity demand due to the so-called electrification of energy sectors. And we want to fill that gap by renewables. There should be done much more. We'll discuss it later when we are in the chapter of the renewable power, such as wind and solar power. And we have also to think about secure infrastructure and operations. So that means we have to increase the power grids, reinforcement of existing lines, enhancement of equipment deployment, energy storage plays a role, and what has been already carried out, smart meters. It's a prerequisite to make dynamic tariffs and create more flexibility. As I mentioned already, we have to do more additions. This doesn't take place in the necessary size. And we have to also map the renewable energy resources and develop a portfolio of financeable projects for medium and long term, construct no new coal power plants and implement end-of-life phase out for coal capacity. This has already been done. A lot of money have been spent there. To my opinion, this money could have been saved just by a sufficient carbon dioxide tax. The use of coal power plants would have been drastically decreased. Update grid planning and accommodate rising shares of renewables for solar and wind. Develop our flexible power systems. We discussed a little bit already. So this means a flexible supply, storage, demand response, power to X. That means we transform electricity via electrolysis into hydrogen or even to methane. The use of electrical vehicles and digital and IT technologies. Update of the so-called grid codes. Deploy microgrids to improve resilience and expand energy access with renewable sources. Deploy supergrids to interconnect regions or even continents. Deploy a cost-effective tariff structure by probably readjusting the balance between volumetric charges, so this means euro per kilowatt hour, fixed charges, so it's cost for the connection or per meter, so euro per meter month, and this has already taken place in the industry. You have some demand charges, so this really depends on the maximum consumption or the maximum consumed power, not energy, but power you have. You have also to pay some charges because the network has to be able to supply that. Yes, support distributed energy, resource deployment, incentivize energy consumption to become so-called prosumers. That means you're not only consuming energy, also you're producing. So if you have a household with a photovoltaic panel on the balcony or on the roof, you are also a generator. And this can save some transmission costs because the share what the consumer is consuming by itself, it doesn't have to be generated, neither transported via the transmission and distribution system. Support regulatory and pricing policy. It's a very important task, non-technical, but rather important, including rights to generate and sell electricity, tariff regulations, and grid arrival policies, and enable energy aggregators to foster the use of distributed energy resources. Come now to another sector, the transportation sector. This is now entirely with fossil fuels, basically the cars. Only the train system is running to some shares with electricity, but this should be increased much more also by the transformation of the car industry into electric car industry. Also, efficiency-wise, it can be done a lot. It's quite easy with electric cars. You have usually an efficiency of battery plus electrical engine in the vicinity of 80%, while you have a fossil fuel car, it's in the vicinity of about 30%. So you have an immediate significant efficiency increase just by switching from fossil fuels to battery cars. Other issue is to reduce transport volume and congestion. So sometimes there's a lot of unnecessary transport is taking place. Sometimes to transport something is cheaper than to store it, which is from the environmental view rather disastrous. And you have to adopt advanced digital communication technologies to improve urban transport planning and services. So rerouting to reduce traffic congestions. Also, if you have share car models, so that it should work in an efficient way. Promote mobility services, for example, autonomous driving, vehicle sharing. Accelerate the shift from passenger cars to public transport. So this is to be made cheaper, but also much more attractive. Deploy low emission city trucks. Accelerate the shift towards electric mobility. So you have to set minimum standards for vehicle emissions. That's already taking place. Give electrical vehicles priority in city access. This also happens in some countries like England, London, downtown, or Zurich, Amsterdam, Copenhagen, and so on. So this is discussed in Germany, but not yet legislated. Incentivize the development of charging infrastructure is also happening at the moment. So you have to also strengthen the links between power and transport sectors with integrated planning and policy designs, vehicle to grid designs. If you imagine that most of the time a vehicle is standing still, either at work or at the office or at home, and during that time the battery is not used, and so if you connect the battery via inverter to the grid, you can supply, for example, storage services or grid supporting services. Yes, for long-term transportation, sometimes a battery is not enough, but at least you should think about biofuels. The same applies for aviation and shipping. So introduce specific mandates to do that for advanced biofuels, accompanied by direct financial incentives and financial de-risking measures. Adopt supporting policies to scale up sustainable production, and eliminate fossil fuel subsidies and implement carbon and energy taxes. So this is not so much in the private transportation sectors, but if you take a look at the aviation industry, they don't have any tax. So this is a kind of subsidy for kerosene. These industry sectors, there can also be a lot done because by large part the energy supply is still by fossil fuels. So we can think about some re-electrification, for example, heat pumps, hydrogen for industrial heat and process, direct use of electricity for industrial heating processes, distributed solar PV and small-scale wind, the direct use of renewables such as solar heating, biomass for process heat, or biomass feedstocks. And a lot of improvement can be carried out by energy efficiencies in the process, by the reuse and recycling in materials, and the use of efficient motors. Building sector, there can also be a lot done by re-electrification as heat pumps, solar rooftops, PV, blending hydrogen in a natural gas for heating, electricity direct use for space heat and water heating and cooking, not as efficient as heat pumps. Heat pumps would be the better option, but usually more efficient than fossil fuel use. Then you can use the renewables directly, also same as in industry, solar thermal for space and water heating, biomass for heating, or biogas for cooking. Can improve energy efficiencies by retrofits of the thermal envelope of the building, high efficiency appliances, and smart homes. So we are at the end of the lecture, and next lecture we will talk about the conventional energy supply such as coal, gas, oil, nuclear. We'll talk about simple thermodynamics, the burning value, and how much water you can heat up by that and so on. We'll talk about the so-called capacity factor. That means how often is the energy available, or how many hours a year is the energy available from a solar power plant, a wind power plant, compared to a coal power plant, for example. And we'll talk about the composition of energy systems, the grid levels, the grid compositions and the voltages, and the daily and seasonal load curves. Thank you very much.